Hello, my name is Jasmine Kim, and I took a database course at Queens College last semester with Professor Peter Heller. I am going to present the final project and what I learned from it. I had to design a database made up of a single table from scratch based on from raw and unorganized data. Here here were the project goals: converting flat file into database, normalization and really formulating relationships between the tables, data cleansing, user-defined data types, data integrity using constraints, store procedures that will insert data into individual tables, and lastly, queries that support the design using JDBC and JTable. Here's an example of flat file, and this was actually the file we received initially. And as you can see, there are no relationships. It's just straight up data, raw, unorganized. And this was the database at the end. And it started with just one table, and you can see that it got split into many different tables and through the process of normalization. And we're gonna go over that next. Normalization is separating one table into multiple tables to reduce data redundancies and insert, delete, and update anomalies. So if you look here, you see that accounting, account ACCT 101, that information is produced multiple times here, and it's prone to redundancies, prone to data anomalies if it's left like this. So it has to, this file and this table needs to be converted, and that's the process of normalization. Removing partial and transitive dependencies, fulfill up to third normal form, which means locating which columns are functionally dependent on which primary key column. For example, we see that we can tell that course description will be functionally dependent on course ID, so it would belong in the course table. And determining the relationships between the tables, which it's going to be child, parent, which table references which table, is there going to be one to many to many relationships, slash, and that requires bridge table. And this was my third draft of the database diagram. It has a mixture of Chen notation and ERD diagrams, so it may not be correct, but it was still work in progress. I had to do this process repeatedly, going back and forth, changing the lines, adding tables, scratching it or erasing it, sorting out the relationships. It was a back and forth process. Um, and determining who becomes parent, who's the child, and which additional tables needed to be created to avoid redundant data. And I think I spent about 4 days on this. I didn't want to start creating something and go back and change things. So I wanted to have like a strong foundation. I ended up doing that anyway, but I think this definitely guided the rest of the project. And in order to start normalizing table, you first have to do some data cleansing. And one of the things that you need to do with data cleansing is identifying and removing the null cells or empty areas. And so I was able to accomplish that with just like a few update statements like this, and kind of replacing just empty no data with TBA, which means to be announced. And another data cleansing thing that I did was atomizing columns with composite data. So here's one example. So this column has not just one kind of information, but it has the department code and it has the course number, and I think it was the credit and hour. So this one is definitely not good, especially if I am going to be inserting data into many different tables. So So in order to ease that or shorten those steps, I just ended up having derived columns for this file. So basically, I revised the file and divided the information into bits and parts. So this way, when we insert data, we can easily refer to a column instead of trying to separate that column each time you refer it. So, and here's an example of user-defined data type. User-defined data type, or UDT, is useful because it allows encapsulation, reusability, and flexibility. It will always have the same definition, default values, and value constraints regardless of where it appears in the database. So it makes the database more uniform and consistent. It also allows flexibility in that it allows the database object designer to model the real world as it exists. So in this case, we defined the data type to be int and we made it not optional but mandatory by saying not null. And here's an example of table definition for the department table. And here's UDT. Yeah, notice that all of the columns are made up of UDTs that have been defined previously, like the previous slide. There is a check on the department code here that it should always start with a capitalized alphabet. It ensures data integrity that way. Here I created a non-clustered index for the department code to ensure uniqueness and to allow faster lookup based on department code such as ACCT instead of department ID. I figured ACCT is more intuitive for people in our minds so that it may be actually used more often than the department IDs when we do queries. There's department table store procedure. And yeah, that this is an example of inserting data from the revised file into the table that I created. Once the table is created with definition, now it needs to be filled with actual data by using a case statement here. Description was added along with the department code. And here's a course table as an example to to share my several thoughts that I had when I was formulating the relationships between the tables. I noticed that a course name is actually composed of a combination of things. So there's a department code and then there's a number. And I figure that the relationship would be that the course has to reference the department code in order to uh, identify its identity. And so you can see here that department ID is used as a foreign key that references the department table from the course table. And here's the course table store procedure. And notice that there is an inner join here with the department code, and course name is made up of, like I said, the main, department code and the just course code. So figure that there was dependency, and so this inner join was necessary. And here's the department instructor bridge table. And this is when I first learned about the bridge table slash association tables. Physical databases don't support many-to-many relationship. So an example is like this one, department and instructors. A department has many instructors, and instructors can be a part of many departments. To support this many to many relationship, a lookup table is necessary, and like this one. So notice the composite primary keys here made up of foreign keys from department and instructor tables. Since the primary keys depend on other tables, this bridge table is considered a weak entity. It has a strongly identified relationship though with the other two tables since it explicitly makes the primary keys based on the columns that it is referencing. The index allows for a faster lookup. The clustered index in the primary key already creates the lookup from department to instructor direction. So I created an alternate index, non-clustered index that allows lookup from the other direction, which was from instructor. Oh, actually, which is from instructor to department ID. Here is a store procedure for the bridge table. Notice that two inner joins were performed to gather data from both tables. It's a lookup table that connects both tables. And here's class table. And as you saw in the rough draft of my database diagram, class was in the center. It served as a child to many different tables. So it's an example of multiple inheritance. It references many other tables. Therefore, you see that there are many foreign key constraints in this table definition. A check was done here to ensure that max enrollment and enrollment number are made up of only numbers because they in from the original table they are strings. So, and here's the class table. um this is the class table description definition, and here's the store procedure. And as expected, many joins are performed to reflect its relationship to other tables. Okay, so I created two queries that support the data design, and I decided to just practice pivot tables. So pivot table is good for data analysis and reporting. How many classes are offered in person, online, hybrid, web enhanced by each department. And that was the proposition. Department ID is accessible by the relationship between class and the course table. Course table has department ID as a foreign key. Class is in between mode of instruction and course tables. So looking at this, class served as like a stepping stone to get to course, and this is how I designed it, and this query supports that design. And here's another query. How many classes are offered by each department? And do some numerical analysis. Obtain a percentage of the current value out of the grand total. So in this query, the database design that is supported by this query is that class is the child and course is a parent and department is the grandparent. Because I set up the relation, I designed the database like this, these inner joins were necessary to obtain that information. Well, the joins were possible because I designed a database like that. And the last part is that I actually run these queries in JDBC. This is my Eclipse, and this first query is the pivot table, and the second query is the data analysis with the grand total and the percentage of the number of classes offered by each department. And let's run it. And here's the J table that came up for the pivot table. And yeah, so you can see how many mode of instructions, what kinds of instructions are offered by each department. It looks like Department 30, and I think that was music. Department offers the most in-person classes, and that makes sense because I think music requires instruments and definitely needs very hands-on instruction. And here's the next table. That was the getting number of classes from each department. Uh, and this time, I guess I actually query the name of the departments too, and I do the data analysis, mm, finding a percentage of the classes offered by each department against the grand total of number of classes offered at Queen's College. And it looks like music department also has many number of classes offered by each department. Yeah. And that was the J table. And going back to the slides, and here's the last one, and just summary and my thoughts. Building database was very challenging, and I'm actually thankful to someone who thought of normalization techniques to avoid duplicate and data anomalies. There are many tools to ensure data integrity, such as setting the data domain and constraints. Also, I realized that uh, creating relationship between the table depends heavily on the business practice. For example, um, numerous bridge tables can be created and is possible among the tables, but is there really a need if the business never have to query that relationship? So this shows the importance of understanding the business and their practice when you're creating the database. And yeah, so the more you know about the business, you can make the database base more efficient for that business. And I also learned firsthand what kind of considerations data scientists have to have or make when designing a database. And also the increasing and efficiency of lookup by creating alternate indexes was a very helpful tip and very practical. And and also yeah. So, yeah, thank you so much for listening to my presentation.